Hey guys, time to dig in on chapter 14, the record of life. So this chapter kind of blurs the lines between biology and geology because we're studying rocks and fossils and things. But again, we're in biology, so we're trying to connect this into life and how life developed here. So science's best methods reveal Earth to be, how old do you think? All right, so about 4.5 billion with a B years old. Okay, so that's old. All right, so the very first part, it was congealing through gravity from all these rocks, and it was really, really, really hot. It was still had all this heat left over from the creation of the solar system. So it was too hot for liquid water. So obviously, before we're going to have living things, we're going to need to have liquid water. Okay, but around 4.4 billion years ago, parts of the planet started to cool down enough, we started to have liquid water. Well, you might be thinking, well, that seems like an almost, that's hardly any time at all. But that is 100 million years, right? A tenth of a billion years is 100 million years. So it's a long time. It took a long time to cool down enough to get a liquid water. So over time, the water is going to kind of collect in the low areas. We're going to get oceans, lakes, aquifers, all the places that water is now. It was starting to accumulate then. Okay, so we start to get liquid water 4.4 billion years ago. The earliest fossils of anything that could really be considered close to human seem like they're only about 200,000 years old. And you'll see different numbers for that because when I say remotely human, different scientists kind of have different ideas about what seems to be... oh wait, that's the wrong blank here. I was jumping up ahead one. This is 3.5 billion years ago. Okay. Sorry, so this is when we start to get liquid water. This is when we start to get evidence of life. Okay, so that's, just a cool 900 million years between liquid water and life. So 900 million. Billion looks super wrong. I feel like I'm spelling it wrong, but I don't know how. It looks very wrong. We're just going to go with it. So by contrast, here's the deal. Human fossils, are about 200,000 years old. And again, I've seen 100,000, I've seen 200,000, I've seen every number in between because it's a gradual change, right? So we see fossils that are like, well, is this human? It's kind of close to human. It's definitely not ape. But it's kind of hard to draw a clear line about what fossils are and are not human. So history in rocks. So we have people whose whole job is to study history of life in rocks, and they're called paleontologists. Okay. If you've ever seen Jurassic Park, at the beginning, they're out at that dig site, and they're trying to dig up dinosaur bones. Those guys are paleontologists. And no, they're not all out in the field trying to find bones, but they are people who study those bones and try to make sense out of those bones in fossils. And I like to think of paleontologists like detectives. Okay, so people like to give the argument of, well, there's no way you can prove life has changed because we can't see it happening. Well, by that measure, you would never ever be able to convict anyone of a crime because you can't go back in time and see them doing it, right? Okay, but we can use the same logic as detectives. It's like we can't go back and watch them do the crime or watch life change, but we can use all the evidence we have to kind of go back and piece things together. So we can't go back in time. It's an impossibility, but they can use clues and evidence to piece things together as best they can. And when it comes to the history of life, there is a lot of evidence to study. Tons and tons and tons. Okay, and what form does most of that evidence take? fossils, which is, for some reason, a really big blank. So fossils are remains of or evidence of ancient organisms that has been preserved somehow. Okay, so all the things that are, living at a certain time, they're all going to eventually die. You'd think we would just be finding fossils everywhere, right? And, by and large, they can find fossils in lots and lots of places. But especially if we kind of think about this, over 99% of all the species that ever existed on Earth are extinct. Okay, so we find lots and lots of fossils, and almost all the fossils we find, those organisms don't exist anymore. Okay, so what happened? Right, where did they go? Okay, and we can look at those fossils and analyze them in a variety of ways, and there's two kind of main ways that we analyze fossils besides just looking at the fossils themselves. But they include what's called radiometric dating. Sometimes it's just called radioactive dating, same idea. And also by just examining the rocks they were found in. Okay, so if you can figure out how old the rocks are, you can also kind of figure out how old the fossils are. Right? So again, this is kind of a key idea here. So most organisms that die do not form fossils. Right? They decompose, their nutrients return to the world, and so the idea that you would have evidence for every living thing that ever existed is pretty far away from the truth. So we say less than 0.01% of things that live and die become fossils. So, and again, less than, I think it's a lot less than, right? So most things that live and die do not become fossils. So if we have a missing fossil, it doesn't mean that organism didn't exist. It just means either A, we haven't found the fossil of it yet, or all that organism died and decomposed, and we might not. Okay, so what has to happen for something to be fossilized rather than to be decomposed? So to something become a fossil, it has to be buried soon after death, and not just buried, but buried in a way that preserves it. Okay, so that is to both stop decomposition, so it's going to limit oxygen to the body, and also to stop scavengers from eating and destroying it. So both of those things are going to be important. Okay, so remember we said there's kind of two ways to figure out how old a fossil is. First kind is called relative dating. And I feel the need to make the requisite joke here that no, this isn't about dating relatives. This is about dating as in figuring out the date that it is from relative to something else. Okay? So think about this, in a dish full of, or sink, in a sink full of dishes, okay, where are you going to find the dishes that have been there the longest? All right, they're going to be on the bottom. Okay, or in a hamper full of dirty clothes, where are you going to find the ones that have been there the longest? The bottom. Okay, the same is true for rocks. Okay, so if you think about any pictures you've seen of like the Grand Canyon, right, there's layers and layers of rocks. And the ones lowest down in the Grand Canyon by where the river's still flowing are really, 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 really old. And the layers of rock closer to the top are only really, really old, right? They're a lot more recently formed. So rock layers are generally older the further down you go. So the deeper you dig, the older of rocks you're going to come across. Again, I would say almost always. So when we use relative dating, we can say things like older than or younger than but that doesn't really tell us how old they are, right? So if I'm looking at layers of rocks here, I can say this is the oldest, and this is the youngest, but I can't say this is 65 million years old, right? I can only say that it is older than these other layers. Okay, so remember the relative here. It is older relative to these other layers, but I don't know how old it is. Okay, if we want to start figuring out actually how old it is, we need to use radiometric dating. Okay, and this is going to use the known decomposition rates of different isotopes of elements to figure out how old something actually is. Okay, and if you don't remember what radioactivity is from physical science, here's your quick recap. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's say this atom, I'll do the actual one. 1, 2, 3, 4, 5, 6, 7, 8. This would be an atom called carbon-14. Okay, that's just the nucleus. I'm not drawing the electrons here. So carbon's atomic number 6, which means it has to have 1, 2, 3, 4, 5, 6 protons. And this dash 14 means its mass, the number of things in the nucleus total, is 14. Okay, this is unstable. Okay, that means radioactive. Means this atom is uncomfortable. It's not stable. It has bad ratio of protons to neutrons. And so over time, it's going to change. Okay, so I still have 14 things there. But after it releases a little radiation, it's going to become, instead of carbon-14, nitrogen-14, which is stable. Okay, so this is radioactive. It's going to break down over time into something that is more stable. All right, so radioactive isotopes break down into more stable things at a, key idea, predictable rate. Okay, it is consistent, it is predictable, it is always the same for a particular isotope. Okay, they measure that rate in what's called half-lives. Okay, which is how long it takes for half of it to break down. And then, again, this is consistent. This is a repeatable kind of experiment that will get consistent results. It's a reliable method here. All right, so we are going to talk about 2 examples because they have different functions in figuring out fossils and things. Okay, so carbon-14, that's the one I drew, breaks down 50%, so again, half-life. Half of it breaks down, 50% of it, about every 6,000 years. Okay. And so carbon-14 is not the main isotope of carbon. Okay, but it is found in a certain concentration in all living things. Okay. So all living things, as long as you're alive and taking in nutrients, you're going to maintain a certain proportion of carbon-14 in your body. Okay? But once you die, okay, you're going to stop taking in new carbon and you're going to have that going away. So when something dies, it stops getting new carbon-14, so how much of it has is going to decrease. Okay, so that amount of carbon-14 is going to decrease over time. And so it is useful for things that lived and died in the last 50,000 years or so. Okay, why only 50,000 years? We'll kind of talk about it on the next page. But if you're getting half of it taken away every 6,000 years, After 50,000 years, you're going to have such a small amount that it's really not measurable anymore. Okay, so the second element that's radioactive that I want to talk about is called potassium-40. Okay, it's not found just in living things. It's found especially in lots of kinds of rocks. And its half-life is much, much longer, 1.3 billion years. All right, so every 1.3 billion years, half of this radioactive isotope disappears. And so it is found in lots of rocks. So a lot of times we use this to figure out kind of how old certain rock layers are, and then we can kind of figure out about how old fossils above or below that rock layer are. Okay, not usually in that rock layer because this is mostly for igneous rock, which forms from lava, which would destroy living things. But we could kind of get a baseline for things that are older or younger than. All right, so we're going to kind of walk through this, hopefully, thing that makes half-lives make a little bit more sense here. Okay, so let's see what we got here. We're going to put half-lives down here. Okay, so remember, each half-life we're going to do it for carbon-14 is like 6,000 years. So we're going to have 1 half-life, 2 half-lives, 3, 4, 5. Let's go out to 6. Why not? And then we're going to have percent carbon-14 left. Okay, so obviously we're going to start with 100%. Okay. So like this would be the moment of death. Okay, so at the moment something dies, it has 100% of the carbon-14 that it had when it died, right? So after, after 1 half-life of time, which would be after 6,000 years, half of that carbon-14 will have decayed. So I go down to where I think 50% would be. There would be my mark. Okay, so that would be 50%. Okay, so you might be tempted to say, okay, so 50% went away after 1 life. After 2 half-lives, it's going to be gone. Okay, but that's not how half-lives work. So after another half-life, half of the remaining carbon-14 will have broken down. Okay, so I go half of the height between this one and this one. So that would be about there. And for my label over here, what would be half of 50? 25. Okay, now we'll keep going here. So another split it in half again. Half of 25 would be 12.5%. And half again, 6.25%. And we can do maybe, one more here. It would be like 3.125%. And then we're getting down to where it's almost getting down to 0. Okay, so if I connect this, we get this nice kind of curve. And it's the kind of thing where, yes, this would maybe go on indefinitely and they would never actually totally reach 0. But again, it's going to reach a point where we couldn't really measure it very well. Okay, so this side represents the carbon-14. Okay, but it's not, remember, it doesn't just disappear, it's becoming nitrogen-14. Okay, so this part, so this starts off pretty small, but then by the end there's a lot, would be the nitrogen-14 because it doesn't go away. Remember, it's transformed. So over time, the ratio, we have lots of carbon-14 and only a little nitrogen-14 at the beginning. As time marches on, we get less and less carbon-14, more and more nitrogen-14 because it's one turning into the other. All right, so how do we use that information? So there's 2 kinds of questions I could ask. Okay, so it says a bone is found with 6.25% the amount of carbon-14 of living things. How long ago did the fossil probably die? Okay, if it's down to 6.25%, right? So it went 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives. Okay, so 4 half-lives. How long is every half-life? Every half-life, remember, is 6,000 years. So, if I didn't misplace my calculator, there it is. So I go 4 times 6,000 years. That living thing probably was alive 24,000 years ago. Okay. Another way you can kind of do these is start with 0 or 100, 50, 25, and just be dividing by 2 every time, right? And then you just count, well, the 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives, and then remember we got to take that times how long is 1 half-life. All right. So the other way we could ask this question, okay, it says what percent of normal carbon-14 would be left after 10,000 years after something would die? Okay, so again, we have to kind of think in our head, okay, 6,000 years. So this is 0 years. 1 half-life would be 6,000 years. So 2 half-lives would be 12,000 years. So it's somewhere between 1 and 2 half-lives. Right? So we can kind of estimate here. So 10,000 would probably be, I'll say right in between. If I went up to the line and over, you know, somewhere between 25 and 50%. So I might say maybe 40%, right? But these are the kind of ones where an estimate is going to be okay, right? You take what you know and you go from there. And you could do the same thing. So 100%, and I would say that's 6,000 years, right? Or 1 half-life. The next half-life will be 12,000 years total. So it's somewhere between 6,000, or sorry, there's 10,000 will be somewhere between there. So it's somewhere between 50 and 25. This is as good a guess as I really would expect from you guys. All right, we're going to stop right there. Always let me know if you have any questions or need any help. We'll see you later.